Every second, ancient light from the dawn of time passes quietly through you. These particles began their journey almost 14 billion years ago, and tonight, without you noticing, they are here. Invisible, untouchable, yet a reminder that even the smallest things can travel unimaginably far. Welcome. I'm glad you found your way here. Before we begin, I'd love to know where and when you're listening from. Midnight in one place, sunrise in another. And yet all of us share this same story of the universe. Share it in the comments if you'd like. It's always amazing to see the many places connected in one quiet moment. This channel is still small, just starting out. And our first milestone is a simple one: to reach 50 subscribers. If you'd like to be part of the beginning, your support means more than you know. Now let's step back in time, all the way to the universe's earliest heartbeat. When people imagine the beginning, they often picture darkness, an empty void. But the truth is stranger. The first universe was filled with light. Not the kind that streams across the sky today, but an ocean of photons so dense, so tightly packed, they couldn't escape each other. Every direction was collisions, every moment a storm of brightness. Light was trapped. Imagine yourself floating in that glow. Not seeing through it because you couldn't. It wasn't clear like sunlight or starlight. It was a fog of brilliance, thick and endless. If you tried to look across it, there would be nothing but a golden white haze stretching forever. A universe not of emptiness but of radiance. This lasted for hundreds of thousands of years. Space expanded, slowly cooling, until at last the storm began to calm. Protons and electrons, which had once been too energetic to stay together, finally joined. The first simple atoms were born, and in that instant, everything changed. The photons, those countless particles of light, were freed. They slipped through the universe, no longer trapped in collisions. They streamed outward, traveling across space and time, and they have never stopped. That glow is still here today, surrounding us, passing through us. Astronomers call it the cosmic microwave background. You might think of it as the first memory of the universe. If you could see it with your eyes, the entire night sky would glow faintly and evenly. No stars, no constellations, just a soft wash of light. It's there, quietly, in every direction. The afterglow of creation itself, but it wasn't perfectly smooth. And that's the reason we exist. Some regions of this ancient glow were just slightly denser than others. Tiny ripples, barely a fraction of a difference. Gravity worked on those ripples, drawing matter together. Over billions of years, those small variations grew into clouds, stars, galaxies, and eventually, the Milky Way, the Sun, the Earth, and you. Think about that for a moment. Your existence depends on imperfection. If the universe's light had been completely uniform, nothing would have formed. No galaxies, no planets, no people. Everything you know began with tiny ripples in that ocean of brightness. Even now, scientists map the sky and find those ripples etched into the cosmic microwave background. They are fingerprints of the earliest universe, still visible, still whispering the story of how structure began. Take a breath and let that sink in. 14 billion years ago, the cosmos released its first light. Tonight, you are touched by it, connected to it, living in its glow. And this is only the beginning. Because in the next part of our journey, we'll move even closer to that first instant, to the moment when space itself inflated faster than light, stretching the fabric of reality and perhaps creating countless universes beyond our own. But for now, let your thoughts rest in the glow of that first light. The cosmos began by shining, and in that light, everything we know was born. The universe had released its first light, but its story stretches back further still, to a time so brief that no human scale can truly describe it. In that very first fraction of a second, the cosmos expanded faster than the speed of light, not because particles raced through space, but because space itself swelled, ballooning at a pace light could never match. This event is known as cosmic inflation, and, though it lasted for less than the blink of an eye, it set the stage for everything we know. Imagine the entire universe smaller than an atom, trembling with restless energy. Then in a sudden burst, it stretched vast and smooth, transforming from something impossibly tiny into something already immense. It is as though reality itself inhaled sharply, and that single breath reshaped eternity. Inflation explains much of what we see in the cosmos today. Across the night sky, galaxies are spread in a way that feels astonishingly even. Stars and clusters appear balanced on the grandest scales, as though laid across a carefully stretched canvas. Without inflation, we would expect chaos, irregularity, great swaths of the universe hotter in some places, colder in others. Instead, when scientists measure the ancient glow of the cosmic microwave background, they find it nearly identical in every direction, like a warm blanket woven evenly across the whole sky. That uniformity is a puzzle, because parts of the universe are separated by distances so great that light could never have traveled between them. There should have been no way for those regions to even out, no way to share conditions. Inflation solves this mystery. Before space ballooned, everything was close together, able to exchange heat and energy. Then, when inflation erupted, those regions were carried apart, stretched beyond one another's reach, yet still bearing the imprint of their shared beginning. Another clue lies in the universe's flatness. If the cosmos were curved like a sphere or saddle, light would bend in measurable ways over great distances. Instead, every observation suggests it is remarkably flat. Inflation explains this too. Just as a balloon appears flatter the more it expands, the rapid stretching of space smoothed out any curves, leaving behind a geometry that seems perfectly level on scales we can measure. The universe, in other words, was ironed flat in its infancy, but perhaps the most profound consequence of inflation is the way it magnified tiny quantum fluctuations. In the earliest universe, space was not perfectly calm. It jittered with microscopic tremors, particles appearing and vanishing in the quantum foam. On their own, these fluctuations were insignificant, but inflation stretched them across the cosmos, turning quantum ripples into cosmic fingerprints. Over billions of years, gravity pulled matter into these faint patterns, growing them into galaxies, stars, planets, and eventually the conditions for life. You and everything you know may trace back to the random whispers of quantum chance amplified in the first instant of creation. Consider how extraordinary that is. The Milky Way, with its spiral arms of stars, began as a faint ripple in the young universe's glow. The sun, warm and steady in our sky, grew from a cloud seeded by one of those ripples. Every atom in your body may owe its place to a fluctuation, smaller than imagination, stretched into significance by inflation's unstoppable rush. Without those imperfections, the universe might have remained featureless, empty, and lifeless. It is not smoothness that gave rise to creation, but imbalance. Existence is built upon imperfection. Some scientists suggest inflation may not have ended everywhere. While it's slowed here, giving rise to our universe, it might still continue in other regions of reality, endlessly creating new spaces, new bubbles, new beginnings. This leads to the concept of the multiverse, an infinite froth of universes, each sealed off from the others by expansion faster than light. In this view, our cosmos, with its 2 trillion galaxies, is just one bubble among countless others. We will never see beyond our own because the runaway expansion locks each bubble inside its own horizon. But imagining this possibility can be humbling. To think of ourselves as not just small within our universe, but part of one among endless
universes, each perhaps with its own laws and its own stars. Picture it like a vast field of flowers.
From where you stand, you can see only the blossoms close to you. Beyond your sight, the field stretches forever, each flower its own world. Our universe is one such blossom, one bloom in a meadow too vast to cross. Inflation suggests that reality
may be this way under a garden of universes, infinite and unreachable yet real. And here is the strangest part. Inflation does not break the laws of physics. The speed of light still holds. Nothing traveled through space faster than light. Instead,
it was space itself that expanded, carrying matter and energy outward. The rule remained unbroken, yet the effect was breathtaking. This is the paradox of inflation. The laws stood firm, but reality transformed in ways that seemed to defy them. So pause and let this settle. In less than a heartbeat, the universe stretched from the smallest scales to cosmic size. It smoothed its wrinkles, scattered its seeds, and set into motion the formation of everything to come. From the tiniest particles to the largest galaxies, the story of all things began with this single surge. As the universe slowed from this furious expansion, conditions shifted again. Gravity began to gather matter, while energy shaped the next chapters of cosmic history. And in this quieter aftermath, new mysteries emerged. Among them, the possibility of black holes formed not from stars, but from the chaos of creation itself. These are called primordial black holes, and if they exist, they are older than any galaxy, older than any star, fossils of the universe's very first heartbeat. As the universe calmed from its first wild expansion, matter and energy began to shape themselves into patterns that would one day become galaxies and stars. But some scientists believe that in those earliest instants, before any atom or star was born, space itself may have collapsed in places so dense that black holes formed. These are not the black holes you may be familiar with, created from the death of massive stars. These are older, stranger, and far more mysterious. They are called primordial black holes, and if they exist, they are fossils of creation itself. Black holes are often imagined as endings, the graves of stars that have burned their fuel and collapsed under their own gravity. But primordial black holes flip that story. They would be beginnings, not endings. Instead of forming billions of years after the universe began, they may have formed within the first second. Imagine regions of the newborn cosmos where matter was packed just a little more densely than average. Gravity in those regions would have been relentless. If the density was high enough, even before stars or galaxies existed, those patches could have collapsed into black holes. Some of these primordial black holes would have been tiny, smaller than mountains, perhaps even smaller than atoms, yet still crushingly heavy. Others could have rivaled stars in mass. Over time, the smallest of them may have evaporated through a process known as Hawking radiation, fading into nothing. But larger ones, if they exist, may still be drifting through the universe today, silent and invisible. Think of what that would mean. Scattered across the cosmos, hidden In its vast darkness, there could be ancient black holes, older than galaxies, older than stars, older than the very light we see in the sky, relics of the first heartbeat of the universe. They would be like cosmic fossils carrying within them the conditions of the very first second after the Big Bang. If we could find them, we might unlock secrets about how the universe truly began. Some scientists even suggest that primordial black holes could explain one of the greatest mysteries in cosmology, dark matter. Astronomers know that galaxies are held together by something unseen, something that outweighs all the stars we can see. They call it dark matter, but its true nature is unknown. Perhaps it is made of exotic particles we have not discovered, or perhaps it is made of countless primordial black holes, invisible but heavy, scattered through the cosmos like hidden anchors of gravity. If that were true, then the oldest objects in the universe might be responsible for shaping its very structure. Galaxies may be strung across the cosmic web not only by invisible particles, but also by ancient black holes guiding their formation like unseen architects. But detecting primordial black holes is a challenge. They do not shine. They emit no light. They drift silently, warping space with their gravity but otherwise hidden. To find them, astronomers must search for their effects. If a primordial black hole passed in front of a star, its gravity could bend the starlight, making the star appear to brighten for a brief moment. This effect, called gravitational microlensing, offers one way to glimpse their presence. Other searches look for the faint whispers of gravitational waves, ripples in space-time produced when black holes collide. If primordial black holes exist, in large numbers, they might merge often, sending out signals that detectors like LIGO and Virgo could pick up. Each ripple would be a message from the deep past, a hint that these ancient objects are real. And yet, so far, no definitive evidence
has been found.
The universe keeps its secrets well. Some cosmologists argue that primordial black holes could make up only a fraction of dark matter, not all of it. Others believe they may be so rare that we will never detect them, but the possibility remains. Haunting. Somewhere out there, drifting in silence, may be black holes that were born before the first star lit the sky. Pause for a moment and try to imagine one. Not a blazing supernova collapsing into darkness, but a patch of the newborn universe, folding in on itself, gravity winning in the chaos of creation. That collapse would leave behind a black hole smaller than a city, yet heavier than a mountain, carrying with it the density of the universe's first instant. Imagine such an object drifting unnoticed through space, invisible but real, older than every galaxy you can see in the night sky. If primordial black holes exist, they remind us that the cosmos is not only filled with light, but also with shadows. Not everything in creation blazes brightly. Some of its oldest relics may be silent, hidden, and almost impossible to detect. And yet without them, the universe might not look the way it does. They also remind us of something deeper. Beginnings and endings are not as separate as they seem. The deaths of stars create ordinary black holes, yes, but the very birth of the universe may have created its own black holes too. Creation and collapse are woven together, part of the same cosmic fabric. So far, the evidence for primordial black holes is elusive, but scientists continue to search. They design new experiments, build more sensitive instruments, and watch the sky for faint hints of these ancient shadows. Perhaps someday we will catch one in the act of revealing itself. Until then, the idea itself is enough to spark wonder. In the end, whether primordial black holes exist or not, the thought is humbling. Somewhere, in the silence between galaxies, there may be objects that have endured since the first second of time. They are older than light, older than stars, older than the very atoms in your body. They are silent witnesses to the universe's earliest heartbeat, still drifting through space like fossils of creation. And as we leave them behind in our journey, we turn to another mystery that may be even stranger. Time itself near the beginning may not have flowed as it does now. In the next part of our exploration, we'll ask, what if time at the dawn of the universe behaved differently, stretching and warping in ways we can barely imagine? We are used to thinking of time as steady. A clock ticks, seconds pass, and one moment follows the next in perfect rhythm. But near the beginning of the universe, time itself may not have behaved this way. The laws that govern our daily lives bend under the extreme conditions of creation. In that first instant, time may have stretched, slowed, or even flowed differently altogether. Einstein's theory of general relativity tells us that space and time are not separate. They are woven together into a fabric called space-time, and the way that fabric behaves depends on energy and gravity. Here on Earth, you notice only the faintest effect. A clock on an airplane runs slightly faster than one on the ground. Near a black hole, time slows dramatically compared to the wider universe. These distortions are real, measurable, and woven into the very structure of reality. Now imagine those effects magnified to the scale of the early cosmos. In the furnace of the Big Bang, densities and energies were unimaginably high. Space-time itself was stretched and twisted. Time may not have flowed evenly from one second to the next. It could have expanded like space did, racing forward in strange rhythms, or slowed almost to stillness. What we call the beginning may not have been the true start, but rather a transition, one phase of existence shifting into another. Some theories even suggest that time as we know it did not exist before a certain point. Before then, there was no before. Asking what happened prior to the Big Bang might be like asking what lies north of the North Pole. The question dissolves because time itself had not yet unfolded into the form we experience. In this view, the Big Bang was not the first event in time, but the moment when time itself began. Other ideas propose that time could be cyclical. Just as seasons repeat, the universe may pass through endless cycles of expansion and collapse, with each Big Bang leading to a new era of time. In this picture, the flow you experience today is just one stream among countless others that have come before and will come again. What feels like a beginning may actually be one chapter in a story without end. Pause for a moment and imagine how unsettling that is. The seconds ticking on your watch, the rhythm of your breath, the beating of your heart, all of it feels steady and certain. But in the crucible of the early universe, none of that steadiness applied. Time may have stuttered, rushed, or warped, changing its character completely. This raises a profound question. Is time something that exists independently, or is it a property that emerges only under certain conditions? Some physicists suspect time is not fundamental at all. Instead, it may arise from deeper layers of reality, like temperature does. A single molecule has no temperature, but a collection of them does. In the same way, perhaps time is not a basic ingredient of the cosmos, but something that appears only when matter and energy arrange themselves in particular ways. If that is true, then the early universe might have been timeless, a state without sequence or duration, until its contents cooled and spread enough for time to emerge. In that sense, the beginning was not a clock starting, but reality shifting into a mode where clocks could exist at all. The consequences of this are staggering. It means the Big Bang may not have been the birth of everything, but the birth of time as we understand it. Beyond it, or before it, may lie states of existence we cannot describe because they are not bound by the same flow. Our language itself fails us, since every word, before, after, beginning, end, assumes time. But if time is not fundamental, then those words have no anchor. And there is another layer still. Quantum mechanics, which governs the smallest scales, does not treat time the same way relativity does. Bringing the two together, quantum physics and general relativity, is one of the great challenges of science. Until we understand how they merge, our picture of time near the Big Bang will remain incomplete. Somewhere in that merging lies the answer to what time truly is and how it behaved in those earliest instants. Pause again and let yourself drift into that thought. The flow of time you feel now, the quiet rhythm of seconds, may be a local illusion, a property of our cooled, expanded cosmos. At the dawn of creation, time itself may have been unrecognizable, a river of strange currents, rapids, and still pools. Or perhaps no river at all, only a vast sea of potential waiting for flow to appear. And think about this. If time is not fundamental, then perhaps endings are not as final as they seem. If the universe began with a transformation of time, it might one day end with another. The heat death of the cosmos, when all energy is evenly spread, may not be the end of everything, but the beginning of another phase, another form of time we cannot yet imagine. The early universe does not just challenge our picture of space, it challenges our picture of existence itself. When we ask what it means for time to begin, we are really asking what it means for anything to be at all. And perhaps in some quiet way, that question will never fully leave us. As we leave this mystery behind, the story widens again. Time shaped the flow of matter, and matter shaped the largest structures in the cosmos. Galaxies did not scatter randomly like grains of sand, but arranged themselves into vast patterns, filaments, walls, and clusters that stretch across billions of light years. In the next part of our journey, we'll look at these enormous structures and discover how the universe is not just vast, but patterned, as though an invisible architecture holds it all together. When you step outside at night and look up, the stars seem scattered, each one shining alone in the dark. But this is only a trick of distance. If you could see the universe from far above, the galaxies would not appear random at all. They would form vast structures connected like threads in a cosmic web, stretching for billions of light years. Astronomers have mapped these patterns using powerful telescopes and sky surveys. What they found is extraordinary. Galaxies gather into clusters, clusters link into superclusters, and those superclusters string together in immense filaments. Between them lie vast empty spaces called voids, some hundreds of millions of light years across. The result is a network that resembles strands of a spider's web or the filaments of neurons in a brain. The universe, on its grandest scales, is not chaos, but architecture. One of the largest known structures is called the Boss Great Wall. It spans nearly 1 billion light years, a chain of galaxy clusters strung together like glowing beads. To put that in perspective, if our Milky Way were a single dot on a page, this wall would stretch across the entire book. Structures like these remind us that the universe is not only immense, but patterned in ways that repeat across scales. The patterns did not arise by chance. They grew from the faint ripples seeded during inflation, those tiny imperfections in the early universe. Gravity amplified the ripples, pulling matter together over billions of years. Regions with just a little more density became the knots, where galaxies formed. Regions with less became the vast voids. Slowly, the cosmic web emerged, a structure billions of years in the making. Pause for a moment and picture it. Galaxies flowing into filaments like rivers of light, superclusters weaving together into walls, and enormous hollows yawning between them. The night sky, from our perspective, shows only scattered stars, but the true design is hidden, too large, to see from within. It is only through maps and surveys that we glimpse the web of which we are a part. Even our own galaxy belongs to this larger architecture. The Milky Way is part of the local group, a small cluster of galaxies bound together. That group, in turn, belongs to the Laniakea supercluster, a vast region spanning over 500 million light-years and containing more than 100,000 galaxies. Our home is just one strand in this immense structure, connected to neighbors we can barely imagine. And yet, even with its patterns, the universe is not static. The structures are still evolving. Clusters of galaxies slowly drift closer, pulled together by gravity, while voids continue to expand as matter flows out of them. Over billions of years, filaments grow sharper, walls become more defined, and the architecture of the cosmos continues to unfold. The web is alive, not frozen, and we are part of its slow-motion growth. This vast design also serves as a laboratory for one of the deepest mysteries in physics: dark matter. Ordinary matter, the kind that makes up stars, planets, and people, is not enough to explain the patterns we see. Something invisible provides the scaffolding on which the cosmic web is built. Without it, galaxies would not have gathered, and clusters would not hold together. Dark matter shapes the largest structures of the universe, silently guiding their formation. Dark energy, too, plays its part. While dark matter pulls galaxies together, dark energy pushes space apart, driving the accelerated expansion of the universe. The balance of these forces writes the script for the web's future. Over time, dark energy will likely stretch the web thinner, pulling galaxies apart until only local clusters remain bound. The cosmic web we see today is temporary, a phase in a story that will eventually change. But for now, we live in a universe richly structured, a universe that repeats itself in echoes both large and small. A single atom has a nucleus orbited by electrons. A galaxy has a core surrounded by stars. A cosmic filament has clusters linked by threads of galaxies. Across scales, patterns emerge, suggesting that structure itself is a fundamental property of reality. Think of the strangeness of this. If you zoom in on a neuron in the brain and compare it to the mapped filaments of galaxies, the resemblance is uncanny. Both are networks of nodes linked by threads, both balance density with emptiness, and both carry the flow of something. In one case, thoughts and signals. In the other, matter and gravity. The universe itself seems to mirror the structure of the mind that studies it. Pause again and let the image of that web settle in your imagination. The galaxies are not scattered dust. They are jewels strung on invisible threads, woven into a design larger than any cathedral, any city, any world. And within one of those galaxies, circling a single star, sits a planet where beings can look up and wonder about the web they cannot see. Our position in this design is humbling. The Milky Way drifts through its filament, pulled by the gravity of countless galaxies carried along in the flow of the larger web. We are not stationary, we are moving, shifting, and weaving with the cosmos itself. Every star you see at night is not fixed, but part of this grand drift. And so as you rest in this thought, remember that you are part of a living architecture. Your body is made of atoms forged in stars. Those stars are arranged in a galaxy, and that galaxy belongs to a filament of the cosmic web. You are woven into the largest structure known, a strand in a design that spans billions of light years. As we leave the cosmic web behind, our journey turns from vast architecture to something even more subtle. For the universe holds not only visible matter but also ghostly particles, relics from its very first second. They stream through you even now, unnoticed, uncounted, but always present. In the next part of our story, we will follow those particles.
The ancient neutrinos that still whisper through space, carrying the memory of the universe's first heartbeat.
Every second, trillions of ghostly particles slip through your body without leaving a trace. They are called neutrinos, and though you do not feel them, they are everywhere, filling the universe in a ceaseless, silent stream. Most of the neutrinos around you come from the sun, from nuclear reactions that light its core. Others are born in distant supernovae or the violent hearts of galaxies. But there is another kind, older and more haunting, neutrinos created in the very first second of the universe, still moving through space today. These are relics of creation itself. To understand them, picture the cosmos when it was less than 1 second old. Temperatures soared to unimaginable levels, and the entire universe was a dense plasma of particles colliding at furious speeds. In that chaos, neutrinos were produced in staggering numbers. Unlike photons, which were trapped by constant scattering with matter, neutrinos interacted so weakly that they slipped free almost immediately, racing outward into space. While light had to wait hundreds of thousands of years to escape, neutrinos fled the furnace within a heartbeat. They have been traveling ever since, nearly 14 billion years later, still whispering through the cosmos and through you. Scientists call this invisible sea the cosmic neutrino background. It is far more elusive than the better-known cosmic microwave background, the ancient light that fills the universe. Photons are relatively easy to detect with telescopes. Neutrinos, however, almost never interact with matter. Trillions pass through Earth every second, and only rarely will a single
One collide with an atom.
This makes them almost impossible to study, yet they are out there in unimaginable numbers, streaming across the universe without pause. Pause for a moment and consider this. Right now, as you listen, countless neutrinos born in the first second after the Big Bang are passing through you. You cannot feel them, cannot see them, but they connect you directly to the earliest moment of time. Every breath you take is crossed by ancient messengers that have been traveling since the dawn of everything. The challenge of detecting them has led to some of the most ambitious experiments in science. Deep underground, inside mountains or buried in Antarctic ice, vast detectors wait in silence. They are designed to catch the rare collisions between neutrinos and ordinary matter. In giant tanks of pure water, sensors look for faint flashes of light caused when a neutrino finally strikes, an atom. Even then, years of waiting may yield only a handful of events. The particles are that elusive. Still, scientists persist because these ancient neutrinos are time capsules. They carry information about the conditions of the universe when it was less than a second old, a period we cannot observe directly in any other way. If we can study them, we might learn how matter first arranged itself, why the universe is filled with more matter than antimatter, and perhaps even what forces shaped the earliest moments of creation. Think of neutrinos as the faintest whispers of the universe's first heartbeat. While photons tell us what the cosmos looked like hundreds of thousands of years after the Big Bang, neutrinos could tell us what it was like in its very first instant. They are messengers from a time before atoms, before stars, before galaxies. They are older than light itself, and they are not only relics of the past. Neutrinos also carry stories of the present. When a star collapses in a supernova, it releases more energy in neutrinos than in light. When nuclear reactions burn inside the sun, neutrinos are the first products to escape. They slip through matter like ghosts, arriving on Earth long before any other signal. In a sense, they are the universe's early warnings, the particles that move freely when nothing else can. But it is the primordial neutrinos that fascinate cosmologists most. Imagine the first second of creation, when space was filled with them, in unimaginable density. Over time, as the universe expanded, they spread thinner and colder, until today, they drift at just a fraction above absolute zero. They no longer carry heat, but they still carry memory. They are fossils, not made of stone, but of pure energy, embedded invisibly in space itself. What is haunting is that you will never escape them. No matter where you go in the cosmos, neutrinos pass through you. They slip through stars, through planets, through galaxies, unhindered by anything in their path. They are everywhere, at every moment, silent companions in the vastness of space. And yet, despite their ghostly nature, they are essential. Neutrinos influence how matter clumps. Together, how galaxies form, and how the universe evolves. Without them, the cosmos might look entirely different. The smallest particles can shape the largest patterns, just as tiny ripples in the early universe grew into clusters of galaxies. Pause again and think of it. Every moment of your life is filled with the passage of ancient neutrinos, relics of the first second after the Big Bang. They are invisible threads connecting you directly to the dawn of time. Every heartbeat, every breath happens within a shower of messengers, older than light, older than stars, older than anything you can see. In the search for them, we see a deeper truth about science itself. To catch even one neutrino from the first second of the universe is to hold a fragment of creation. It is like hearing the faintest echo of a song sung billions of years ago, still carrying across the void. As we leave neutrinos behind in our journey, the story grows larger again. For even today, entire galaxies may be moving under the influence of hidden masses beyond the edge of what we can see. This strange effect, called the dark flow, suggests that the universe we observe may be only a fragment of a greater whole, tugged by invisible forces from beyond our cosmic horizon. And it is there that our path now leads. The universe feels vast enough when we look at the stars above, but there are hints that what we see is only a fraction of a larger reality. Astronomers studying the motion of galaxies have discovered something strange. Entire clusters containing thousands of galaxies are not drifting in the directions expected. Instead, they seem to be pulled toward a mysterious point in space, a motion so large it has been nicknamed the dark flow. To understand why this is puzzling, imagine floating in a calm lake. The water should carry you gently, evenly, with small ripples and currents. Now imagine the whole lake tilting slightly so that everything drifts in one direction. That is what astronomers see in the cosmos. Galaxies are not simply expanding outward with the universe as they should. Many appear to be flowing together as if pulled by something massive beyond the edge of what we can observe. The cause of this flow is unknown. One possibility is that enormous concentrations of matter exist outside our cosmic horizon. These hidden giants, invisible because their light has not yet reached us, might be tugging on galaxies across billions of light years. If true, then the observable universe, everything we can see, is only a patch in a much larger whole, influenced by structures forever beyond our reach. Pause for a moment and let that sink in. Entire galaxies, each containing billions of stars, are sliding through space because of something we cannot see. They move not randomly, but with purpose, drawn toward an unseen presence. The universe is not only larger than we can observe, but also shaped by regions we will never know directly. Scientists measure this dark flow by studying the cosmic microwave background, the afterglow of the Big Bang. As galaxies move through space, their motion leaves faint imprints on this ancient light. By analyzing those imprints, astronomers detect the collective drift of galaxies toward the same region of sky. The effect is subtle, but it persists. Something is pulling. Some suggest it could be massive clusters lying just beyond the observable horizon, their gravity strong enough to reach across the gulf. Others wonder if it hints at something even stranger. Perhaps another universe pressing against ours, its presence felt only through gravity. Whatever the explanation, the dark flow is a reminder that the cosmos is larger than we can ever see, and that the edges of our vision are not the edges of reality. Imagine standing on the shore of the ocean. From your perspective, the horizon is the limit. You cannot see beyond it. Yet you know the sea continues, stretching far past your sight. The cosmic horizon works the same way. It is not the boundary of space, only the limit of what light has had time to reach us. Beyond it, galaxies, clusters, and perhaps even larger structures still exist. And those structures may be tugging on us even now, their gravity shaping the motion of galaxies across the visible sky. Think of the scale involved. The Milky Way itself is moving at more than 1,000,000 miles per hour, carried along in this drift. We, our solar system, our planet, are sliding through the universe because of something invisible and unreachable. Every star you see at night is moving too, part of this hidden current flowing toward an unknown destination. For some, this raises unsettling questions. If the universe is infinite, filled with countless regions beyond our view, then what lies out there? Are there structures so vast they make our great walls and superclusters look small? Could other universes with their own galaxies and laws of physics press against ours, their presence detectable only through faint gravitational tugs?
The dark flow may be a whisper of realities larger than anything we can imagine.
Others argue that the effect may not be as strong as first thought, that more precise measurements could explain the motions without invoking hidden masses. Science, as always, demands caution. Yet the possibility remains open, and it lingers.
In the imagination, something unseen is shaping what we see, and the mystery is far from solved. Pause again and let yourself feel it.
Right now, as you breathe, as your heart beats, as you rest in this moment, your galaxy is drifting through space at incomprehensible speed, pulled by forces from beyond the horizon. You are moving only because Earth orbits the Sun, or because the Sun orbits the Milky Way, but because the Milky Way itself is being tugged toward a hidden mass. You are part of a current that stretches across billions of light years, a cosmic tide guided by unseen shores. The dark flow teaches us something profound. The universe is larger than observation. Our telescopes, no matter how powerful, are bounded by light and time. Yet gravity is not so limited. Its influence can cross horizons, reaching us from places we cannot see. In that way, we glimpse the existence of more than we can measure. This realization humbles us. We live in a bubble of visibility, surrounded by galaxies, stars, and clusters. But outside that bubble lies a greater cosmos, one that still leaves fingerprints on our world. The night sky you see is not the whole story, it is only the part revealed by light. The rest, hidden masses, perhaps hidden universes, tugs at us quietly, reminding us that we are part of something far larger. And so the dark flow is not only an astronomical puzzle, it is a philosophical one. It asks us to accept that reality is bigger than we can ever witness, that some truths lie beyond evidence, reachable only through inference and imagination. It is an invitation to humility, to wonder, and to curiosity. As we leave this mystery, we turn to another that may be even more puzzling. For the universe is not only influenced by hidden structures, it is also shaped by an invisible force that fills all of space, pushing galaxies apart and accelerating expansion. In the next part of our journey, we explore dark energy, the most mysterious ingredient of the cosmos, and the invisible hand that may decide its ultimate fate. For most of history, people assumed the universe was steady and eternal, an unchanging backdrop against which stars and galaxies lived out their stories. But modern astronomy tells a different tale. The universe is expanding. Galaxies are drifting farther apart with time, carried on the swelling fabric of space itself. And, stranger still, this expansion is speeding up. The cause is something we cannot see, cannot touch, and cannot fully explain. It is called dark energy, and it makes up nearly 70% of the cosmos. The discovery came only a few decades ago. Astronomers measuring distant supernovae expected to find that cosmic expansion was slowing under the pull of gravity. Instead, they found the opposite. The galaxies were receding faster than before. Something was pushing space outward, driving acceleration. This invisible pressure, spread evenly across the universe, is what we call dark energy. Pause to think about that. Most of the cosmos is made not of stars, planets, or even dark matter, but of something even more elusive. Every cubic inch of space is infused with it. Even the emptiest regions where no galaxy shines are alive with this hidden energy. We cannot see it, yet it is the dominant force shaping the future of everything. What exactly dark energy is remains one of the greatest mysteries in science. Some suggest it is the energy of the vacuum itself, a restless hum of quantum fields that fills space even when it appears empty. Others propose it may be a new kind of field, something woven into the fabric of reality but not yet discovered. Whatever its nature, its effect is clear. It stretches the cosmos apart. The implications are staggering. If dark energy continues as it does now, the universe will keep expanding forever. Galaxies will drift apart, stars will burn out, and over.
Trillions of years, the cosmos will fade into a cold, dark silence.
This is known as heat death, not a fiery ending, but a slow dissipation of all usable energy until nothing remains but scattered particles in endless night. But dark energy may not stay constant. Some theories suggest it could grow stronger with time. If that happens, expansion would accelerate more and more until even galaxies, stars, and eventually atoms are torn apart. This scenario is called the Big Rip, a catastrophic unraveling of reality itself. Everything, down to the smallest particles, would be pulled apart by the relentless surge of expansion. Other theories imagine the opposite. Perhaps dark energy could weaken, allowing gravity to halt expansion and reverse it. The universe might then collapse inward in a big crunch, erasing galaxies and stars in a final blaze of heat. From that collapse, some suggest a new Big Bang could emerge, beginning the cycle again. Expansion, collapse, rebirth, an eternal rhythm of cosmic bounces. Whichever path is true, dark energy holds the answer. The ultimate fate of the universe depends on its hidden nature. And yet, despite decades of study, we are only beginning to glimpse what it might be. Pause again and feel the weight of this mystery. Right now, as you sit in this moment, galaxies billions of light years away are accelerating outward, carried by an invisible pressure. Every second, the universe grows larger, not just in space, but in possibility. And within that expansion lies the question of how everything ends. Scientists probe dark energy by studying the large-scale structure of the cosmos. They map how galaxies cluster, how light bends as it passes through space, and how the cosmic microwave background holds subtle imprints of expansion. These measurements act like fingerprints, clues that may reveal what dark energy truly is, yet for now, the puzzle remains unsolved. What makes dark energy so haunting is its quietness. It does not blaze like a star or roar like a supernova. It is silent, steady, everywhere at once. It shapes the cosmos not through bursts of power, but through constant presence. It is the background force of existence, a whisper strong enough to decide the destiny of everything. And in a way, this makes it deeply poetic. The fate of galaxies, the flow of time, the story of creation itself, all are tied to something invisible, something we cannot touch but must trust is there. The universe is vast, not only in size but in mystery, filled with forces that lie just beyond our grasp. Imagine the distant future. Galaxies so far apart that their light no longer reaches each other. Stars long extinguished, their remnants cooling into silence. Planets frozen, atoms decaying, space stretched into emptiness. This is one possible end, a universe not with a bang, but with a long, gentle fading. Or perhaps the future will be more violent, with everything torn apart in the big rip or compressed in the big crunch. Each possibility flows from the same question. What is dark energy? We may never know the answer fully, but even in our uncertainty, there is beauty. The very act of asking ties us to the cosmos. To wonder what drives expansion is to place ourselves in the story of everything, to recognize that the same laws guiding galaxies guide us too. Dark energy is not only a scientific puzzle, it is a reminder of our place. We live in a universe that is unfinished, still unfolding, still revealing itself. And whether it fades, rips, or rebounds, we are part of that story, written into the same expansion that carries galaxies across the night sky. As we leave this invisible force behind, we turn to another mystery. Not about what lies ahead, but about what lies beneath. For even empty space is not truly empty. At the quantum level, the vacuum itself seethes with energy, particles flickering in and out of existence. In the next part of our journey, we explore the quantum vacuum, the restless sea of nothingness that may hold the key to dark energy itself. When most people picture empty space, they imagine a perfect void, silent, cold, and barren. But physics paints a different picture. Even in the most complete vacuum, space is not truly empty. Instead, it is restless, filled with invisible fluctuations. Tiny particles and antiparticles flicker into existence, borrow energy from uncertainty itself, and vanish again in less than a blink. This seething background is called the quantum vacuum, and it may hold the key to some of the greatest mysteries in cosmology. At first glance, the idea sounds impossible. How can nothing contain energy? But in quantum mechanics, uncertainty rules. Energy cannot be pinned down to absolute zero. Instead, fields hum with potential, producing brief sparks of particles that appear and disappear too quickly to be directly observed. Though fleeting, their influence is real. They affect the behavior of atoms, alter the orbits of electrons, and even generate measurable forces between objects. Pause and consider that. What do you think of as emptiness? The silent gap between stars, or the airless void beyond Earth's atmosphere, is not empty at all. It is alive with invisible activity, a constant buzz beneath the surface of reality. Every cubic inch of space, no matter how empty, holds this restless hum. The implications stretch to the largest scales of the cosmos. Many physicists suspect that dark energy, the mysterious force accelerating cosmic expansion, may be the energy of the vacuum itself. If true, then every patch of space carries with it a hidden pressure, and as space expands, more vacuum is created, more energy fills the universe, and expansion accelerates further. The fate of galaxies may be written not in stars or matter, but in the invisible fabric of emptiness. This idea also ties to the earliest moments of creation. Inflation, that rapid expansion in the first fraction of a second, may have been driven by vacuum energy. If so, the very birth of the universe was powered not by matter, but by the energy of nothingness. In that sense, the vacuum is not emptiness at all, but the most creative force imaginable, capable of birthing universes. And yet, a deep paradox lingers. When physicists calculate the vacuum energy predicted by quantum theory, the result is absurdly large, far greater than what we
observe in cosmic expansion.
The mismatch is colossal, one of the greatest unsolved problems in physics. Why is the vacuum energy so small in practice when theory suggests it should be enormous? Somewhere in this puzzle lies new physics, waiting to be uncovered. Pause again and think of what this means. The emptiness around you is not empty. It hums with invisible fields, it shapes the cosmos, and it may even decide the fate of the universe. To sit in silence, to breathe in stillness, is to be surrounded by activity too subtle to sense, yet fundamental to reality itself. This restless vacuum has other consequences. It gives rise to phenomena like Hawking radiation, the faint glow predicted, to leak from black holes. Near the event horizon, quantum fluctuations allow pairs of particles to form, with one falling into the black hole and the other escaping as radiation. Over immense timescales, this process could evaporate black holes entirely, all of it driven by the energy of the vacuum. The vacuum also underpins the Casimir effect, a force that appears when two metal plates are placed extremely close together in a vacuum. The plates limit which quantum fluctuations can exist between them, creating an imbalance that pushes the plates together. This strange, subtle force has been measured in laboratories, proof that the quantum vacuum is not just theory but a physical reality we can detect. What is most haunting is how the
Vacuum blurs the line between nothing and something.
In ordinary experience, nothing means absence, but in physics, nothing is never truly nothing. It is potential, restless, alive. The universe itself may have emerged from such a fluctuation, a quantum tremor magnified by inflation into the vast cosmos we inhabit. If so, then everything you see, galaxies, stars, life, grew out of the hum of nothingness. Imagine it. A single fluctuation, one spark of quantum uncertainty, blooming into all that exists. The story of reality may not be that something came from nothing, but that nothing was never truly nothing to begin with. And this is where the quantum vacuum connects directly to human existence. Every atom in your body was forged in stars, every star born from clouds of gas, every cloud shaped by gravity, and gravity itself sculpted by the expansion of space. All of it, ultimately, rests on the restless hum of the vacuum. You are here not in spite of nothing, but because of it. Pause one more time and let that settle. The silence between breaths, the quiet of the night sky, the dark between galaxies. It all hums with hidden life. To rest in stillness is to float in an ocean of invisible energy, a sea that may be the true foundation of reality. As we leave the quantum vacuum, the story turns again toward light. Not the light of stars or galaxies, but the oldest light in existence, the cosmic microwave background, faint radiation that carries patterns written when the universe was still young. In those subtle ripples lie clues to events that happened before the Big Bang itself, echoes of a time we may never fully see. And it is to those ripples, those fingerprints of creation, that we now turn. When you tune an old television to static, a tiny fraction of that hiss comes from the afterglow of the universe itself. This faint radiation, stretched into microwaves by billions of years of expansion, is called the cosmic microwave background. It is the oldest light we can see, released when the universe was only a few 100,000 years old. To the eye, it looks uniform, a gentle glow spread evenly across the sky. But hidden within it are patterns, ripples so faint they differ by less than 1 part in 100,000. Those ripples are the fingerprints of creation. They tell us where matter was slightly denser, where gravity would one day draw galaxies together, and where voids would open. Every star, planet, and life form owes its existence to those tiny variations. Without them, the universe would have remained smooth and featureless, with no clumps to ignite into stars. Imperfection, not perfection, made creation possible. But some of the ripples are stranger than expected. Among the faint patterns lie unusual alignments, cold spots, and anomalies that do not fit the simplest models. These features hint that the story of the universe may stretch back even before the Big Bang. One such feature is known as the cold spot, a vast region of the sky where the microwave background is significantly cooler than its surroundings. Some suggest it is caused by a massive void in that direction, a hollow so large it saps energy from photons as they cross it. Others believe it could be a scar, an imprint left by a collision with another universe. If true, then the cold spot may be evidence that our cosmos is not alone, but one bubble in a greater multiverse. Pause and imagine that. The afterglow of the Big Bang, mapped across the sky, carrying hidden scars from collisions with universes we can never see. The light that surrounds you may hold messages not only from the birth of our cosmos, but from realities beyond it. Another puzzle is the so-called axis of evil, a name given to a strange alignment in the large-scale patterns of the microwave background. Instead of being random, some of the ripples line up along a common direction. This should not happen in a universe that is uniform on large scales. The cause is unknown. It could be a statistical fluke, an artifact of measurement, or something far deeper, new physics from the earliest moments of inflation. These anomalies remind us that the microwave background is not just a relic of the past, but a window into mysteries we do not yet understand. Within its faint glow may lie evidence of events before the Big Bang itself, echoes of a reality that existed before time as we know it began. Pause again and think of the strangeness of this. Light that has been traveling for nearly 14 billion years now reaches your eyes, carrying with it subtle ripples from a universe not yet formed. To see the microwave background is to see not just light, but history stretched across the sky like a cosmic memory. Scientists study these ripples with exquisite precision. Satellites like COBE, WMAP, and Planck have mapped the microwave background in detail, revealing its tiny fluctuations. Those maps are like baby pictures of the cosmos, showing what it looked like when it was only a few 100,000 years old, and in those pictures are clues to everything that followed: the density of matter, the shape of space, the seeds of galaxies, and perhaps even hints of what came before. Some theories suggest that inflation, that brief, violent expansion in the first instant, left behind faint imprints in the microwave background. If so, the ripples are not just patterns of matter, but fossils of quantum fluctuations, stretched across the sky by inflation. In this view, every galaxy that exists today grew out of the smallest possible tremors of uncertainty, magnified to cosmic scales. And then there are the more speculative ideas. Some physicists propose that unusual features in the microwave background could be evidence of cosmic strings, defects in space-time left over from the early universe, like cracks in cooling ice. Others suggest that the ripples may carry hints
of physics beyond our current understanding, perhaps even clues to dimensions we cannot see.
What is certain is that the microwave background is a treasure. It is the oldest light we can observe, a direct message from the young universe. Without it, we would be blind to our origins. With it, we can trace the story of how the cosmos became what it is today. Imagine standing beneath a night sky, not with stars, but with the entire dome glowing faint orange, as it would have billions of years ago when the microwave background was still visible to the naked eye. The universe itself once shone like a sun, bathing everything in light. That glow has cooled and stretched, fading into microwaves invisible to human eyes. But it has not disappeared. It still surrounds you, silent and patient, carrying the memory of beginnings. As you listen now, the cosmic microwave background is streaming through you, through the room around you, through Earth itself. It is everywhere, the same in every direction. A reminder that we are bathed in ancient light at all times, and so the ripples in that light become more than data. They are whispers of creation, scars of ancient events, and perhaps hints of realities beyond. They tell us that imperfection built the universe, that collisions may leave echoes across time, and that even nothingness can remember. As our journey continues, we leave the oldest light and turn to something even more elusive: particles. We have not yet discovered particles that may decide the fate of everything. In the next part of the story, we will explore the possibility that the destiny of the universe rests on hidden matter, unseen forces, and particles still waiting in the shadows of physics. The destiny of the universe is not decided by the stars you see, nor even by the galaxies that fill the sky. It rests instead on things we cannot yet detect, particles that may or may not exist, hidden forces that shape the future in silence. The universe's fate, whether it expands forever, collapses back, or cycles through endless rebirths, depends on mysteries still locked away in the unseen. Dark energy is one of them, but not the only one. Dark matter, too, is essential. It outweighs the visible matter of stars and planets by more than 5 to 1. Without it, galaxies would not hold together, clusters would fly apart, the cosmic web would never have formed. Yet we still do not know what dark matter actually is. Some experiments suggest it could be made of heavy, slow-moving particles that rarely interact with ordinary atoms. Others propose it could be something far stranger: ultralight particles spread like invisible waves across space, or even primordial black holes formed in the first second after the Big Bang. Each possibility leads to a different vision of the universe's future. If dark matter is made of certain unstable particles, it could eventually decay, altering the balance of forces across cosmic time. If it is made of stable particles, the cosmic web may remain intact for trillions of years. If it is made of black holes, their slow evaporation through Hawking radiation could seed the very last whispers of energy in a dying universe. Pause for a moment and consider how fragile this balance is. The largest structures in existence, the filaments of galaxies spanning billions of light years, depend on particles too small to see. The fate of everything may lie in physics still waiting to be discovered. The search for these hidden particles is ongoing. Deep underground, detectors shielded from cosmic rays wait for the faintest collisions between dark matter and ordinary atoms. Particle accelerators like the Large Hadron Collider probe the smallest scales of reality, hunting for exotic particles that could explain the invisible. Astronomers scan the sky for signs of gravitational lensing, where unseen masses bend the light of distant galaxies. Each method is a way of listening for whispers from the dark. The answers will not only reveal what dark matter is, but also whether the universe is stable. Some theories suggest that our cosmos rests in a metastable state, like a ball balanced on the edge of a hill. A slight push caused by quantum effects or new physics could send it tumbling into a lower state, rewriting the laws of nature as it spreads. This idea, known as vacuum decay, would erase the universe instantly, replacing it with something unrecognizable. It is unlikely in the near term, but the possibility is haunting. Even without such catastrophes, the ultimate fate depends on these
unseen forces. If dark energy remains steady, expansion continues forever. If it grows stronger, the Big Rip tears everything apart. If it fades, gravity could pull the cosmos back together.
The difference between these futures may come down to particles we have not yet found. Pause again and let the strangeness of that settle. You are living in a universe whose future has not yet been written. It depends on discoveries still to be, made on experiments deep underground, on collisions in accelerators, on the faintest ripples of gravity measured by distant detectors. The fate of all things is tied to knowledge we do not yet hold. Some physicists suggest that the universe may cycle endlessly, reborn after each death. If so, new physics will decide how that rebirth happens, whether through a collapse and bounce or through quantum tunneling into a new state. In this view, our universe is just one chapter in an infinite book, its ending determined by rules still hidden in the dark. Others imagine that our cosmos is a simulation, its fate written not in particles but in code. If so, then the laws of physics are simply the rules of the program, and the end will come when the simulation ends. It is speculative, but it reminds us that what we call reality may not be the final layer. What all these possibilities share is humility. We cannot yet say how the universe will end because we do not yet know what it is made of. But each clue we uncover brings us closer. Each particle discovered, each anomaly measured, each experiment refined narrows the possibilities. The future may be hidden, but it is not unknowable, and in this uncertainty lies something beautiful. The universe is not a finished story. It is a mystery unfolding, and we are part of its discovery. The same forces that shape galaxies shape us. The same particles that decide the fate of the cosmos pass through your body every moment. To wonder about the end of the universe is to wonder about your own place in it. As our journey continues, we turn from the vast to the subtle, from galaxies and particles to the quietest force of all, gravity. We think of it as universal, but compared to the other forces of nature, it is astonishingly weak. A small magnet can lift a paperclip against the pull of the entire Earth. Why is gravity so faint? Some physicists believe the answer lies in hidden dimensions, unseen layers of reality where gravity slips away. And it is there, into these hidden realms, that we now move. Gravity feels like the most familiar of forces. It holds your body to Earth, guides the moon around our planet, and binds the planets to the sun. On cosmic scales, it sculpts galaxies, drives the orbits of stars, and anchors black holes. And yet, when compared to the other forces of nature, gravity is astonishingly weak. A simple kitchen magnet can lift a paperclip against the pull of the entire Earth. Why should the force that holds the universe together be so faint? Physicists have puzzled over this imbalance for decades. Electromagnetism, the strong nuclear force, and the weak nuclear force are all vastly stronger than gravity, even though they act only at small or atomic scales. Gravity alone seems diluted, stretched thin across existence. One possible explanation is that gravity is not confined to the universe we see. Instead, it may leak into hidden dimensions, spreading its strength into realms we cannot perceive. These hidden dimensions are not science fiction, but serious ideas in theoretical physics. String theory, for example, suggests that the universe may have more than the familiar 3 dimensions of space and 1 of time. There could be additional dimensions curled up so tightly that we cannot see them, smaller than the smallest particle. Gravity, unlike other forces, may seep into those dimensions, explaining why it feels weaker in our own. Pause and imagine that. Every time you drop something, every time Earth holds you to its surface, the pull you feel may be only a fraction of gravity's true strength. The rest could be flowing into invisible directions, shaping a reality broader than we can perceive. This idea also carries profound implications for cosmology. If gravity spreads into extra dimensions, then the large-scale
structure of the universe may not follow the rules we expect.
Galaxies might move differently, black holes might behave in unexpected ways, and the ultimate fate of the cosmos could be altered by influences from beyond our visible space. Some experiments are already searching for evidence. Sensitive instruments test how gravity behaves at very small scales, looking for deviations from Newton's law that might reveal hidden dimensions. Particle colliders probe for exotic particles that could slip between dimensions, and gravitational wave detectors may one day sense distortions caused by effects beyond the 4 dimensions we know. Even if these dimensions remain hidden, the possibility forces us to think differently about space itself. What we call reality may be only a surface, a slice of something richer and more layered. We live in 3 dimensions, not because that is all that exists, but because that is all we can access. Pause again and let that settle. The ground beneath you, the space around you, the sky above you, all could be part of a larger framework, one where unseen dimensions fold and curl beyond perception. Gravity may be the only clue, whispering of realities that stretch deeper than our senses. Some theories suggest that entire universes could exist within these hidden dimensions, stacked alongside our own, like pages in a book. If true, our cosmos may not be the whole of reality, but one layer among countless others. Gravity, faint as it seems, could be the thread that connects them. Even if such ideas remain unproven, they remind us of the humility science demands. The universe is vast not only in size but in possibility. What feels familiar may be only a fragment of truth. What feels complete may be only the beginning. The weakness of gravity may not be a flaw but a clue, pointing us toward deeper layers of reality waiting to be uncovered. As our journey continues, we move from the pull of hidden dimensions to the limits of sight itself. For even with the most powerful telescopes, we cannot see beyond the cosmic horizon, but a boundary set not by distance, but by time. And yet, just as hidden dimensions expand reality inward, the cosmic horizon expands it outward, reminding us that what we see is
only a fraction of what exists.
It is to this horizon, and to the unseen regions beyond it, that we now turn. When you stand on a shore and gaze across the sea, the water seems to end at the horizon. Of course it does not. The ocean stretches far beyond what you see, but your perspective is limited by distance and the curve of the Earth. The universe has its own horizon, not of water and sky, but of space and time. It is called the cosmic horizon, and it marks the limit of what light has had time to reach us since the beginning. Look deep into the night sky, and you are looking back in time. The farther away an object is, the older the light you see, but there is a boundary to this backward glance. The universe is 13.8 billion years old, and light travels at a finite speed. Beyond a certain distance, there simply has not been enough time for light to cross the gulf and reach us. Those regions are real, filled with galaxies, but they are hidden forever beyond our sight. This boundary is not static. Every year, more ancient light arrives, expanding the observable universe. Yet space itself is also expanding, carrying galaxies farther away. Some regions recede faster than light, not by breaking physics, but because the fabric of space between us stretches. Those galaxies slip beyond our horizon, lost forever. The cosmic horizon, then, is not a wall but a shifting boundary between the known and the unknowable. Pause and imagine that. No matter how powerful our telescopes become, there will always be more universe beyond reach, receding into darkness. The horizon is not just a limit of technology, but of nature itself. This raises haunting questions. If the universe beyond our horizon is real, what does it contain? More galaxies, more clusters, more cosmic web, perhaps even structures larger than anything we have ever imagined. Some scientists suggest that regions beyond could be very different, with different densities, different patterns, even different physics. Others believe the universe is uniform on the largest scales, stretching endlessly in every direction, the same beyond the horizon as within it. The truth may never be known. The cosmic horizon also forces us to confront the scale of reality. The observable universe already spans 93 billion light-years across, containing 2 trillion galaxies. And yet this immense expanse may be only a tiny fraction of the whole. Just as the ocean stretches beyond the shore, the cosmos may continue without end beyond the edge of what we see. Pause again and let that sink in. Every star you have ever seen, every galaxy mapped by astronomers, every nebula captured by telescopes, all of it is only one patch of a larger fabric. To gaze at the sky is to see only the nearest threads of an infinite tapestry. This horizon is not just a boundary of sight, but a boundary of knowledge. We build our cosmology, our understanding
of the universe from what we can observe. Yet what lies beyond could be vastly different.
It could hold clues to mysteries we cannot solve, or it could hide contradictions to everything we believe. The cosmic horizon humbles us, reminding us that our maps are always incomplete. There is beauty in this limitation. It means the universe always holds mystery. No matter how far we explore, no matter how much we learn, there will always be more beyond. The horizon is not an ending, but an invitation to wonder, to imagine, to recognize that reality is greater than our grasp. Some theories even suggest that entire other universes could lie beyond our horizon, sealed off by expansion. If inflation continues in distant pockets, new universes may be budding endlessly beyond our sight. In this picture, our cosmic horizon is not just a limit of vision, but a boundary between worlds. We live in one bubble, surrounded by others we will never touch. And yet, for all its vastness, the horizon is also intimate. Right now, as you listen, light from galaxies billions of years away is streaming toward you, carrying messages from the edge of the observable universe. You are not separate from the horizon, you are at its center. Everywhere in the universe has its own horizon, its own bubble of sight. From the perspective of another galaxy, their horizon looks different. In that sense, horizons are not absolute, but personal. The universe is stitched together from countless overlapping spheres of vision, each centered on a different point of existence. This thought is humbling. You, here, are the center of your observable universe. Every direction you look, the horizon stretches equally away. You are not the center of everything, but you are the center of your everything. The same is true for every star, every galaxy, every listener across time. Each place is central, each horizon unique, each perspective valid. As we close this part, Of the journey, let the idea of the horizon linger. It is the line between the known and the unknowable, the seen and the unseen, the present and the forever hidden. To live beneath the cosmic horizon is to live with mystery, to be reminded that reality is larger than sight, deeper than knowledge, and richer than imagination. From here, we turn from horizons to relics. If the cosmic horizon hides what we cannot see, primordial black holes may hide what we cannot remember. Fossils from the universe's first heartbeat, hidden across the cosmos, carrying secrets older than stars. Black holes are usually thought of as the corpses of stars born when massive suns collapse under their own weight. But some black holes may be older than stars, older even than galaxies. These are called primordial black holes, and they may have formed in the very first second of the universe's existence. If they exist, they are fossils of creation itself. In the chaos after the Big Bang, matter and energy were not spread evenly. Tiny fluctuations meant that some regions were denser than others. If a patch of space was dense enough, gravity could have pulled it together before atoms or stars ever
Formed.
Instead of clouds of gas, these regions may have collapsed directly into black holes. Unlike stellar black holes, which form from dying suns, these primordial black holes would carry the imprint of the earliest universe. Pause and imagine that. Scattered across the cosmos could be relics from the first instant of time, silent travelers as old as reality itself. While stars are born and die, galaxies collide and drift apart. These black holes could persist, unchanged, older than any other.
Object in existence, their possible sizes are just as strange.
Some theories suggest they could be microscopic, with horizons smaller than an atom. Others could weigh as much as mountains or even stars. The smallest would have evaporated through Hawking radiation long ago, but larger ones might still be, drifting through space today, invisible except through their gravity. If primordial black holes exist, they could solve one of the deepest mysteries in cosmology, the identity of dark matter. Dark matter outweighs visible matter by more than 5 to 1, shaping galaxies and clusters, yet it has never been directly detected. Perhaps it is not made of exotic particles at all, but of countless ancient black holes, scattered like hidden anchors across the universe. Scientists search for them in subtle ways. If a primordial black hole passes in front of a star, its gravity can bend the starlight, an effect called micro-lensing. Surveys scan the sky for such flickers, hoping to catch one. Other searches look for the faint radiation that evaporating black holes would release. Each possible signal is a chance to glimpse these relics. So far, the evidence is uncertain. No clear detection has been made, but neither have they been ruled out. The universe is vast, and primordial black holes could be hiding anywhere, drifting through interstellar space, passing quietly through galaxies, or even wandering near our own solar system. Pause again and let that thought settle. Right now, a primordial black hole could be passing unnoticed through the outskirts of the Milky Way, a silent fossil from the dawn of time. It would be too small to see, too quiet to detect, yet powerful enough to hold secrets from before the first stars. If discovered, these black holes would change everything. They would give us direct evidence of conditions in the earliest universe, a time we can otherwise only model with equations. They would confirm that gravity sculpted reality from its first instant, collapsing matter into objects that still survive. Today, they would also reveal whether dark matter is made of particles or of black holes, solving a puzzle that has haunted science for decades. The existence of primordial black holes also raises profound questions about survival. If tiny black holes still exist, could they ever collide with Earth? The answer is almost certainly no. The universe is unimaginably vast, and the chance of Such an encounter is vanishingly small, but the idea is haunting that invisible objects older than time could drift silently through the cosmos, indifferent to stars, planets, and life. And yet, perhaps that indifference is part of their meaning. They remind us that the universe does not revolve around us. It began long before we existed and will continue long after. Primordial black holes are not threats but markers, proof that creation leaves behind fossils, that even chaos can write memories into reality. Pause once more. To look at the night sky is to see stars, galaxies, and nebulae. But somewhere in the darkness may lie objects with no light, no glow, no surface. Objects that predate everything you see, carrying in their silence the story of beginnings. As our journey continues, we leave these hidden fossils and turn to another possibility from the universe's birth: cosmic string. Not black holes, not matter, but cracks in space-time itself, stretching across the cosmos like scars of creation. In the earliest moments of the universe, as it cooled from an unimaginably hot beginning, strange defects may have formed in the very fabric of space-time itself. These are called cosmic string, not strings of matter, but cracks in the geometry of reality. Infinitely thin, yet immensely powerful, they could stretch for billions of light years, relics of phase transitions when the young cosmos shifted from one state to another. To picture them, imagine water freezing into ice. As it solidifies, cracks and imperfections form in the surface. The universe too may have gone through such transitions, and cosmic strings would be the scars left behind. They are not physical objects in the way stars and planets are, but disruptions in the underlying fields that govern physics. If they exist, cosmic strings would be astonishingly dense. A piece as thin as a proton could outweigh mountains. There, gravity would be immense, bending light and matter around them. Galaxies passing near one could appear doubled as their light split into arcs and illusions. They would not shine, but their presence would be unmistakable. Pause and imagine one stretched across the night sky. You would not see it directly, but the stars near it would appear duplicated, their light bent by its gravity. A silent scar across the heavens, invisible but powerful. Cosmic strings could also snap. If two strings crossed and reconnected, or if a loop broke apart, the release of energy would ripple through the universe as bursts of gravitational waves. These ripples might still be detectable today, faint tremors from events billions of years old. Scientists are already listening for them using detectors like LIGO and pulsar timing arrays to catch the faint hum of cosmic strings vibrating across space-time. The discovery of such waves would change everything. It would confirm that the universe carries scars from its birth, evidence that physics once operated under conditions unlike anything we can reproduce. It would also open a window to energies far beyond current experiments, a glimpse into forces that shaped the cosmos before atoms existed. Pause again and consider the possibility. Right now, cosmic strings may be threading the universe, silent. Filaments of broken symmetry stretching farther than galaxies. They may be hidden in the dark, influencing matter, shaping structures, leaving echoes we have not yet learned to hear. Though no cosmic string has been confirmed, their existence would connect cosmology to particle physics in a profound way. They would be proof that the universe still remembers its earliest transformations, that the fabric of reality itself can hold memory. And even if they are never found, the search reveals something essential. The universe is not only vast, but layered with possibility. What looks smooth may hold scars, what looks silent may hum with hidden vibrations, what looks stable may carry ancient fractures from the dawn of time. From these cosmic scars we turn to another kind of ripple, not in matter or strings, but in space-time itself. Gravitational waves, first detected from colliding black holes, may also carry the faintest echoes of the universe's birth, vibrations older than galaxies, older than stars. And it is to those primordial ripples that we now turn. Ripples in space-time are not just a theory anymore. In 2015, scientists announced the first direct detection of gravitational waves, tiny distortions in the fabric of the universe caused by two black holes colliding over 1 billion light-years away. The signal was faint, stretching, and squeezing. Space by less than the width of a proton, yet it confirmed a prediction Einstein had made a century earlier. Suddenly, space-time itself became something we could listen to. But long before black holes collided, long before galaxies formed, the universe itself may have trembled with waves far older, primordial gravitational waves. These are thought to have been born in the first instant after the Big Bang, during cosmic inflation. When the universe expanded faster than light, quantum fluctuations in space-time could have been stretched to cosmic scales, creating ripples that still echo across reality today. Unlike light, which could not travel freely until hundreds of thousands of years later, these primordial waves would carry us back almost to time zero. Detecting them would be like hearing the heartbeat of creation itself. Pause and imagine that. The universe vibrating in its first instant, those vibrations frozen into space-time and still ringing across the cosmos 13.8 billion years later. Scientists are searching for them not with ordinary telescopes, but by studying the faint polarization patterns in the cosmic microwave background. If gravitational waves rippled through the early universe, they would have twisted the alignment of ancient light in subtle ways. Experiments at the South Pole, in high-altitude balloons, and in satellites orbiting Earth all scan the sky, hoping to catch the fingerprint of those ancient tremors. The search is difficult. The signals are faint, drowned out by cosmic dust and other noise. Yet even a whisper of success would transform cosmology. It would confirm inflation, reveal the energy, scales of the early universe, and perhaps point to new physics beyond anything we know. Pause again and let the scale of that sink in. With a single detection, we could reach back farther than any telescope, farther than any particle collider, to the very moment reality began. Primordial gravitational waves would also teach us about the forces that shaped the universe. Were they born from inflation alone, or from exotic events like cosmic strings snapping, or even from transitions between hidden phases of physics? Each possibility leaves a different signature in the waves. To decode them would be to read the first chapter of existence. Even if we never detect them directly, their possible presence reshapes how we see the cosmos. The universe is not silent. It rings with vibrations, from colliding stars to the faint hum of space-time itself. To live in such a universe is to exist inside a cosmic symphony, most of it too faint for our ears, but real all the same. Consider for a moment that as you sit here now, gravitational waves are passing through you, stretching and squeezing space by imperceptible amounts. They pass through Earth, through your body, through everything. You cannot feel them, but they are there, whispering of distant collisions and ancient beginnings. This perspective is humbling. You are not separate from the cosmos. You are immersed in its vibrations, carried along in its rhythms. To detect primordial waves would not only be a scientific triumph, but also a reminder of connection, that from the very first instant, the universe has been ringing, and you are part of that music. As we leave these faint tremors behind, our path turns towards something closer to home, yet just as mysterious. Galaxies, including our own, are not drifting randomly through space. They are being drawn ever so slowly toward an unseen destination, a region known only as the Great Attractor, a gravitational enigma hidden in the depths of the universe. The existence of primordial black holes also raises profound questions about survival. If tiny black holes still exist, could they ever collide with Earth? The answer is almost certainly no. The universe is unimaginably vast, and the chance of such an encounter is vanishingly small. But the idea is haunting, that invisible objects older than time could drift silently through the cosmos, indifferent to stars, planets, and life. And yet, perhaps that indifference is part of their meaning. They remind us that the universe does not revolve around us. It began long before we existed and will continue long after. Primordial black holes are not threats but markers, proof that creation leaves behind fossils, that even chaos can write memories into reality. Pause once more. To look at the night sky is to see stars, galaxies, and nebulae. But somewhere in the darkness may lie objects with no light, no glow, no surface. Objects that predate everything you see, carrying in their silence the story of beginnings. As our journey continues, we leave these hidden fossils and turn to another possibility from the universe's birth: cosmic string. Not black holes, not matter, but cracks in space-time itself, stretching across the cosmos like scars of creation. In the earliest moments of the universe, as it cooled from an unimaginably hot beginning, strange defects may have formed in the very fabric of space-time itself. These are called cosmic string, not strings of matter, but cracks in the geometry of reality. Infinitely thin yet immensely powerful, they could stretch for billions of light years, relics of phase transitions when the young cosmos shifted from one state to another. To picture them, imagine water freezing into ice. As it solidifies, cracks and imperfections form in the surface. The universe too may have gone through such transitions, and cosmic strings would be the scars left behind. They are not physical objects in the way stars and planets are, but disruptions in the underlying fields that govern physics. If they exist, cosmic strings would be astonishingly dense. A piece as thin as a proton could outweigh mountains. There, gravity would be immense, bending light and matter around them. Galaxies passing near one could appear doubled as their light split into arcs and illusions. They would not shine, but their presence would be unmistakable. Pause and imagine one stretched across the night sky. You would not see it directly, but the stars near it would appear duplicated, their light bent by its gravity. A silent scar across the heavens, invisible but powerful. Cosmic strings could also snap. If two strings crossed and reconnected, or if a loop broke apart, the release of energy would ripple through the universe as bursts of gravitational waves. These ripples might still be detectable today, faint tremors from events billions of years old. Scientists are already listening for them using detectors like LIGO and pulsar timing arrays to catch the faint hum of cosmic strings vibrating across space-time. The discovery of such waves would change everything. It would confirm that the universe carries scars from its birth, evidence that physics once operated under conditions unlike anything we can reproduce. It would also open a window to energies far beyond current experiments, a glimpse into forces that shaped the cosmos before atoms existed. Pause again and consider the possibility. Right now, cosmic strings may be threading the universe, silent. Filaments of broken symmetry stretching farther than galaxies. They may be hidden in the dark, influencing matter, shaping structures, leaving echoes we have not yet learned to hear. Though no cosmic string has been confirmed, their existence would connect cosmology to particle physics in a profound way. They would be proof that the universe still remembers its earliest transformations, that the fabric of reality itself can hold memory. And even if they are never found, the search reveals something essential. The universe is not only vast, but layered with possibility. What looks smooth may hold scars, what looks silent may hum with hidden vibrations, what looks stable may carry ancient fractures from the dawn of time. From these cosmic scars we turn to another kind of ripple, not in matter or strings, but in space-time itself. Gravitational waves, first detected from colliding black holes, may also carry the faintest echoes of the universe's birth, vibrations older than galaxies, older than stars. And it is to those primordial ripples that we now turn. Ripples in space-time are not just a theory anymore. In 2015, scientists announced the first direct detection of gravitational waves, tiny distortions in the fabric of the universe caused by two black holes colliding over 1 billion light-years away. The signal was faint, stretching, and squeezing. Space by less than the width of a proton, yet it confirmed a prediction Einstein had made a century earlier. Suddenly, space-time itself became something we could listen to. But long before black holes collided, long before galaxies formed, the universe itself may have trembled with waves far older, primordial gravitational waves. These are thought to have been born in the first instant after the Big Bang, during cosmic inflation. When the universe expanded faster than light, quantum fluctuations in space-time could have been stretched to cosmic scales, creating ripples that still echo across reality today. Unlike light, which could not travel freely until hundreds of thousands of years later, these primordial waves would carry us back almost to time zero. Detecting them would be like hearing the heartbeat of creation itself. Pause and imagine that. The universe vibrating in its first instant, those vibrations frozen into space-time and still ringing across the cosmos 13.8 billion years later. Scientists are searching for them not with ordinary telescopes, but by studying the faint polarization patterns in the cosmic microwave background. If gravitational waves rippled through the early universe, they would have twisted the alignment of ancient light in subtle ways. Experiments at the South Pole, in high-altitude balloons, and in satellites orbiting Earth all scan the sky, hoping to catch the fingerprint of those ancient tremors. The search is difficult. The signals are faint, drowned out by cosmic dust and other noise. Yet even a whisper of success would transform cosmology. It would confirm inflation, reveal the energy, scales of the early universe, and perhaps point to new physics beyond anything we know. Pause again and let the scale of that sink in. With a single detection, we could reach back farther than any telescope, farther than any particle collider, to the very moment reality began. Primordial gravitational waves would also teach us about the forces that shaped the universe. Were they born from inflation alone, or from exotic events like cosmic strings snapping, or even from transitions between hidden phases of physics? Each possibility leaves a different signature in the waves. To decode them would be to read the first chapter of existence. Even if we never detect them directly, their possible presence reshapes how we see the cosmos. The universe is not silent. It rings with vibrations, from colliding stars to the faint hum of space-time itself. To live in such a universe is to exist inside a cosmic symphony, most of it too faint for our ears, but real all the same. Consider for a moment that as you sit here now, gravitational waves are passing through you, stretching and squeezing space by imperceptible amounts. They pass through Earth, through your body, through everything. You cannot feel them, but they are there, whispering of distant collisions and ancient beginnings. This perspective is humbling. You are not separate from the cosmos. You are immersed in its vibrations, carried along in its rhythms. To detect primordial waves would not only be a scientific triumph, but also a reminder of connection, that from the very first instant, the universe has been ringing, and you are part of that music. As we leave these faint tremors behind, our path turns towards something closer to home, yet just as mysterious. Galaxies, including our own, are not drifting randomly through space. They are being drawn ever so slowly toward an unseen destination, a region known only as the Great Attractor, a gravitational enigma hidden in the depths of the universe. The Milky Way, along with its neighboring galaxies, is not drifting aimlessly through space. It is moving at more than 1 million miles per hour, pulled by something massive and unseen. Astronomers call this mysterious source the Great Attractor. When scientists first mapped the motion of galaxies in the 1970s, they noticed something strange. Whole clusters were not moving as expected. Instead, vast regions of space appeared to be sliding in the same direction, as though drawn down a hidden slope of gravity. This flow could not be explained by the galaxies and clusters we could see. Something larger and more massive seemed to be exerting its pull. Pause and imagine that. Our entire galaxy, with its 200 billion stars, its planets, its nebulae, its black holes, everything you have ever known, is in motion, carried toward an invisible destination. The Great Attractor lies in the direction of the constellations. Centaurus and Hydra, about 150 to 250 million light-years away. But studying it is difficult because it is hidden behind the plane of the Milky Way. Our own galaxy's dust and stars block much of the view, creating what astronomers call the zone of avoidance. Even so, evidence suggests that the Great Attractor is part of a vast concentration of galaxies, clusters, and dark matter, perhaps an entire supercluster region pulling us in. The scale is hard to grasp. The Great Attractor's gravitational influence spans hundreds of millions of light years, shaping the flow of galaxies far beyond our local group. We are not alone in being drawn toward it. Thousands of galaxies share the same motion, sliding along cosmic filaments toward a shared destination. What exactly is the Great Attractor? That question remains open. Some see it as a dense knot in the cosmic web, a region where filaments of galaxies converge. Others believe it is part of an even larger structure called the Laniakea supercluster, a gravitational basin that contains our Milky Way and hundreds of thousands of other galaxies. In this view, the Great Attractor is not a single object, but a region of deep gravitational influence, like a valley in the landscape of space-time. Pause again and consider the implication. The universe is not static. Galaxies are not frozen in place. They drift and flow, pulled along invisible currents of gravity. The Milky Way is just one among billions, carried on a journey it cannot escape, guided by structures larger than imagination. For us, this motion is invisible. The night sky looks still, the stars unmoving. But when astronomers measure the cosmic microwave background, they can see the signature of our galaxy's drift. It appears as a subtle dipole. One side of the sky slightly warmer, the other slightly cooler, caused by our motion through space. It is the fingerprint of the Great Attractor written into the oldest light in the universe. The thought is humbling. Every star you see, every constellation, every story ever told beneath the night sky, all of it is moving slowly but surely toward a hidden destination. The Great Attractor reminds us that we are not anchored, we are travelers, part of a vast migration of galaxies flowing along the currents of cosmic gravity. Some speculate that the Great Attractor is only part of the story. Beyond it may lie even greater structures, unseen masses pulling on galaxies across unimaginable distances. Already, astronomers speak of the Shapley supercluster and other regions of density even farther away, perhaps extending the flow beyond what we can map. The true destination of our galaxy may be hidden behind layers of larger and larger attractors, like rivers feeding into oceans we cannot yet chart. Pause once more. To live on Earth is to feel stable, rooted, unmoving. But in truth, you are carried through space at tremendous speed, drawn by forces beyond sight. The Great Attractor is a reminder that stillness is an illusion, that motion defines the universe, and that we are part of that endless drift. From this hidden pull, we now turn to an even stranger force, one not of attraction, but of expansion. While gravity draws galaxies together, dark energy pushes them apart, accelerating the universe's growth. Its strength may decide not only where we are going, but whether the cosmos will tear itself apart in the end. In the late 1990s, astronomers made a discovery that changed cosmology forever. They had been measuring the brightness of distant supernovae, expecting to find that the universe's expansion was slowing down under the pull of gravity. Instead, they found the opposite. Expansion was speeding up. Galaxies were not just drifting apart, they were accelerating away from each other as if pushed by an invisible force. That force is what we now call dark energy. Dark energy is not like anything we experience. It is not matter, not light, not radiation. It seems to be a property of space itself, a kind of pressure that causes space to expand faster the more of it there is. Imagine drawing dots on a balloon. As you blow it up, the dots spread apart. Now imagine that the balloon's rubber itself is stretching faster and faster, driven by some hidden energy. That is the effect dark energy has on the universe. Pause and reflect on this. More than 2/3 of the cosmos is made of something we cannot see, cannot touch, and barely understand, yet it shapes the destiny of everything. What is dark energy? The truth is, no one knows. Some theories say it is the energy of empty space itself, the quantum vacuum bubbling with virtual particles. Others suggest it is a dynamic field, slowly changing over time. A few even propose that our understanding of gravity is incomplete, and what we call dark energy is really a sign of deeper physics waiting to be discovered. What matters most is how it behaves. If dark energy remains constant, the universe will continue expanding forever, galaxies drifting farther apart until trillions of years from now, the night sky goes dark as their light fades beyond our horizon. If dark energy grows stronger, expansion will accelerate catastrophically. Galaxies will be torn from one another, stars ripped from galaxies, planets from stars, and eventually atoms themselves pulled apart in a final big rip. If dark energy weakens or reverses, gravity could slow expansion, perhaps even pulling the universe back into a collapse, a big crunch. Pause again and let those possibilities sink in. Everything, from the largest galaxy cluster to the breath in your lungs, depends on the nature of something we cannot see. Right now, evidence suggests that dark energy is steady, behaving like a cosmological constant. But even the tiniest variation could change the outcome. A difference in the 100th decimal place might mean the difference between eternal expansion and eventual collapse. To measure it precisely is one of science's greatest challenges. Astronomers use multiple approaches to study it. They map how galaxies cluster over billions of years, tracing how expansion has stretched the cosmic web. They measure the faint imprints of baryon acoustic oscillations, ancient sound waves frozen in the distribution of galaxies. They even use gravitational lensing, watching how dark matter bends light, to infer how expansion has evolved. Each method narrows the possibilities, but the mystery remains. Pause once more. Imagine that the fate of the universe is written in numbers so small we can barely detect them. Our entire cosmic future depends on parameters buried deep in the equations of physics, waiting for us to uncover them. Dark energy also raises profound philosophical questions. Why now? For billions of years, gravity and matter dominated. Only recently, on cosmic timescales, has dark energy become the most powerful influence. Why do we live in the moment when expansion accelerates? Is it coincidence, or does it point to deeper principles, perhaps even a multiverse where different universes carry different balances of energy? Whatever the answer, dark energy ensures that the cosmos is not static. It is restless, expanding faster each day, shaping a future very different from the past. To live in such a universe is to live in a place where change is woven into the fabric of space itself. As we leave the mystery of dark energy behind, we turn to a quieter but equally vast phenomenon: the great voids of the universe. Between the luminous filaments of galaxies lie immense expanses almost completely empty, silent hollows where darkness rules. These voids, though seemingly vacant, hold keys to the nature of expansion itself. When we picture the universe, we often imagine it filled with galaxies, spirals, clusters, glowing webs stretching in every direction. But between those filaments of light lie vast expanses of near nothingness, regions called cosmic voids. These are not small gaps, but enormous hollows, some hundreds of millions of light years across, where galaxies are sparse and matter is thin. They are the dark counterbalance to the bright architecture of the cosmic web. At first glance, voids may seem unimportant. After all, what could emptiness teach us? Yet it is precisely their emptiness that makes them valuable. In these regions, matter is so scarce that the effects of dark energy and cosmic expansion are easier to see. While galaxies tug on one another, with gravity, voids expand more freely, like balloons swelling in the spaces between clusters. Studying them allows scientists to test how the universe grows and how dark energy shapes its rhythm. Pause and imagine drifting inside one of these voids. You would travel for millions of light years without seeing a single galaxy. The stars would thin until they disappeared, leaving only blackness and silence. It would be the loneliest journey imaginable, a plunge into the vast hollows of creation. But voids are not completely empty. They contain faint wisps of gas, the occasional dwarf galaxy, and the invisible scaffolding of dark matter. These sparse inhabitants reveal that voids are part of the same cosmic web as everything else, just stretched thin by expansion. In fact, the boundaries of voids are often where galaxies cluster most strongly, drawn together as matter flows away from the emptiness. Voids also challenge our intuition. On Earth, emptiness feels fragile, temporary, waiting to be filled. But in the cosmos, voids grow larger with time. As expansion continues, matter drains from these regions, flowing toward denser filaments and clusters. In a sense, voids are the universe's growing wounds, widening as the cosmos ages. Scientists study them in creative ways. They map galaxies across the sky, looking for gaps in the distribution. They watch how light from distant quasars dims or shifts as it passes through near-empty space. Even gravitational lensing can reveal voids, bending light less than expected, creating subtle fingerprints of absence. Pause again and let this idea sink in. The universe is not only shaped by what exists, but also by what does not. The great hollows are as real as the galaxies. and together they form the pattern of reality. Voids also highlight the fragility of existence. If the cosmos were only slightly different, if matter had spread more evenly after the Big Bang, there might be no great structures at all, no filaments, no voids, just a smooth haze. Instead, we live in a universe where contrast defines beauty. Galaxies and clusters shining against a backdrop of immense nothingness. There is also something strangely poetic about them. In the same way silence gives shape to music, voids give shape to the cosmos. Without them, galaxies would not gather into walls and filaments. Without emptiness, structure would lose its meaning. The universe needs its hollows as much as its stars. Some even wonder if voids hold deeper mysteries. Could dark energy behave differently inside them? Could they magnify subtle effects of gravity or expansion? In their silence, might they carry the faintest echoes of physics we have not yet discovered? For now they remain among the quietest places in existence, and yet they remind us that absence can be as powerful as presence, that the universe is sculpted not only by light and matter, but by vast oceans of darkness. From these great voids we turn at last to the shape of the whole. Is the universe flat, curved, or something stranger? Its geometry may seem abstract, but hidden within it lies the answer to whether the cosmos is infinite, finite, or destined to close back upon itself. When you look up at the night sky, it feels natural to think of the universe as endless, stretching flat in every direction. But geometry is more subtle than our eyes can sense. The shape of the cosmos, whether flat, curved like a sphere, or bent like a saddle, determines not only how galaxies move, but whether the universe is infinite or finite. To test its shape, scientists turn to the oldest light, the cosmic microwave background. This faint glow from 380,000 years after the Big Bang is imprinted with tiny ripples, frozen patterns of density. If the universe were curved like a sphere, light from those ripples would bend inward, making the patterns appear larger than expected. If it were curved like a saddle, the patterns would appear smaller, stretched outward. By measuring them with exquisite precision, we can read the geometry of the cosmos itself. The results are astonishing. To the limits of observation, the universe appears flat, not curved inward or outward, but balanced almost perfectly on the line between. This flatness is so precise that if the universe has curvature, it is too small to detect. Imagine standing on Earth and looking around. From your perspective, the ground feels flat, though you know the planet is curved. In the same way, the universe may be curved on scales far beyond what we can see, but within our horizon, it looks flat. Pause and let that sink in. On the largest scales we can measure, reality aligns itself with straight lines, as though the cosmos has been smoothed and stretched into balance. This is no accident. Inflation, the rapid expansion in the universe's first instant, would have flattened any initial curvature, leaving behind the nearly perfect geometry we see today. But what does flatness mean for destiny? A flat universe that keeps accelerating under dark energy may expand forever, thinning into silence. If dark energy changes, the story could shift. But flatness alone suggests that the cosmos is vast, possibly infinite, with no edge and no boundary. Pause again. Try to imagine infinity. Galaxies without end, stars upon stars, no wall, no edge, no outside. It is almost impossible to grasp. Our minds are shaped for limits, but the universe may offer none. Geometry also touches something deeper: perspective. Just as every point in space sees itself at the center of its own horizon, every observer also sees the universe as balanced around them. Flatness is not only a property of space, but also a reminder that our place in the cosmos is not special. No matter where you stand, the universe stretches equally outward. Yet even here, mysteries remain. Some anomalies in the cosmic microwave background hint at possible curvature or strange alignments. Whispers that the universe's geometry may hold surprises still hidden. Others suggest that what we call flatness may itself be part of a larger structure, a bubble in a multiverse, flat inside but curved in relation to other realms beyond. Pause one final time. Whether infinite or finite, curved or flat, the universe has carried us from a blazing beginning to a still expanding present. Along the way, we have seen light trapped like matter, time warped near the Big Bang, galaxies drawn by hidden attractors, voids widening into silence, and energy pushing space apart. Through it all, one truth stands out. The cosmos is vast, mysterious, and beautiful beyond measure. And here you are, listening now, a small part of it, yet inseparable from the whole. The atoms in your body were forged in stars, the light in your eyes has crossed billions of years, and your thoughts are carried on the same laws that guide galaxies. To reflect on the geometry of the universe is to realize that you too are written into its shape. So let this journey settle within you. The universe is flat, or perhaps curved in ways we cannot see. It is finite in what we observe, but maybe infinite in truth. And whether it ends in silence, collapse, or renewal, it is a story that connects you to everything. Thank you for being here, for listening, for joining this small circle as we explore the cosmos together. Tonight we close our journey, but the universe does not close. It expands, drifts, and sings on. And perhaps as you drift into rest, you can feel that same expansion inside you. A widening calm, a reminder that you are part of something greater, something that began long before and will continue long after. Sleep well, and until next time, keep wondering.